Hello everyone, thanks for coming to the Australian Geometric PDE seminar for today. Today we've got Ben Andrews who will be telling us about all the fun things you can do with Ricci flow in 2 dimensions. Thank you, Ben.
Thanks, Tim. Yeah. So 2 dimensions, things are in a way more complicated, although of course in many ways much simpler than the things we've been talking about here. Okay, so Ricci flow on surfaces. So most of what I'm going to talk about goes back to the paper by Hamilton, which I think is a beautiful paper to read, and I really encourage you to do that. I won't completely stick to what he does, but there's some really beautiful ideas in there which I will try and bring up. All right, so in 2 dimensions, the big simplification, of course, is what happens to the curvature tensor. And that is our curvature tensor, instead of being really a 4-index thing, is completely determined by just one scalar function. So it really, I can write it like this. It's just determined by this function k, the Gauss curvature, which is the, well, k is, I mean, given this form, it's just the R1, 2, 1, 2 in any orthonormal frame. And so it's just the, the one sectional curvature of the tangent plane, sectional curvature of the tangent space. Okay, so then that means we just have this Gauss curvature function k, and if I take the trace of that equation, then I get that the Ritchie curvature is just Gauss curvature times the metric, and the scalar curvature, given the trace of the Ritchie, would be then twice the Gauss curvature, 2k. So the Ritchie flow becomes the following equation. So ddt of g is, so it's minus 2 Ritchie, so that's just minus 2, minus 2k gij. So in particular, I mean, one of the nice things about this is that this is a conformal flow. So it just changes the metric by, adding a multiple of the metric, some smooth function times the metric. So that tells us that the metric at any time is a multiple of the initial metric. So it's convenient to write that as, say, e to the 2u. Okay, so this will depend on x2. Let's say g of xt will be some function e to the 2u xt times the initial metric gx0. Okay, so really this is a conformal flow. I mean, so there's the result that lies behind this is the so-called uniformization theorem. This is sort of the 2-dimensional version of geometrization in some sense, but it goes back a lot further, of course. So this is well, Poincaré and Kerber in 1907. Okay, and I guess the motivation for this was due to Felix Klein a little bit earlier on. So this just says, at least in the language that I want to use, any metric on a compact 2-surface, compact 2 manifold, is conformal to a constant curvature metric. So this would be just constant k metric, constant sectional curvature. All right, so this is something which you can prove using the Ritchie flow, and I guess I'll give a proof using the Ritchie flow. So the idea is that you start with an arbitrary metric and you deform it by this Ritchie flow, which moves in the conformal class, and will take you eventually to a constant curvature metric. Okay. So that's what I'll try to prove. There's various cases of this, as I'll show you. All right, so first of all, just a couple of quick comments on the the sort of geometric computations here, which also, because of the conformal nature of it, become quite simple in this case. So if you have conformal metrics, particularly in 2 dimensions here, so if I have a metric G, which is given in this way, so e to the 2u times some other metric G bar, then you can write the Gauss curvature of the new one in terms of the old one and the conformal factor, right? So it says the Gauss curvature of G is given by, okay, so I take e to the minus 2u times the Gauss curvature of G bar minus the Laplacian of u with respect to G bar. Okay, and it's worth remarking here that the Laplacian itself in 2 dimensions has a nice sort of conformally invariant structure. So if I take the Laplacian with respect to G of a function, then that is just given by e to the minus 2u times the Laplacian with respect to G bar. Okay, so essentially the Laplacian is the same operator, just gets multiplied by a smooth function. And you can see that by looking at the expression for the Laplacian local coordinate. So the Laplacian of f with respect to some metric, I can write as, so 1 over the square root of the determinant, let's just say in any local coordinates, determinant of the metric times the ith partial derivative of square root determinant times G inverse ij times the jth partial derivative. Okay. Now, if you change the metric conformally in 2 dimensions, then the change in the change in this square root of the determinant will cancel out the change in the G inverse. Right? So the part inside the bracket here doesn't change. And so the only change you get from changing the metric in this way is this term in the front. So that gives this e to the minus 2u. So yeah, that's special to 2 dimensions. We get this beautiful conformal invariance for the Laplacian. Okay, so let me go then to the normalized Ritchie flow. So I guess we've looked at this before, but in the 2-dimensional case, this is particularly simple. So remember, okay, well, let me just remind you how the derivation of this normalized flow goes. But we're going to rescale the metric to make the area fixed. So let's suppose we have a solution of the unnormalized Ritchie flow. So let me call that G tilde or something like that, because I want to eventually work with things without tildes. So my unnormalized things are going to be G tildes. So if I have d by d tau of G tilde ij is, so this is evolving by Ritchie flow. This is just minus 2 Gauss curvature tilde times G tilde ij. Then I want to define new metrics just by rescaling. So G is going to be, so I'm going to rescale to, let's say, area 4 pi, just to be concrete. So to do that, I take 4 pi divided by the area measured with respect to G tilde times G tilde. Right? So you can, if you think about it, that's exactly the factor you need to make the area of the resulting metric equal to 4 pi. So we're imposing this condition. The area with respect to G is 4 pi. And then if I work out the derivative with respect to tau of this G, the rescaled thing, okay, so I get the 4 pi divided by mg tilde times the time derivative of G tilde, which is minus 2 k tilde G tilde. Okay, and then I'll get the term coming from the derivative of the area element, and that will give me plus 2, we write it as kappa G, where kappa here is just the average of the Gauss curvature. So here. Okay. Right. So, and now I define the new time variable by d by dt is mg tilde over 4 pi times d by d tau. Okay, and that just cancels off the term at the front, and I end up with this normalized Ritchie flow. So this is 2D normalized Ritchie flow is d by dt gij is minus 2 k minus kappa gij. Okay, so the normalization here. So the important thing in 2 dimensions is that in 2 dimensions, we've got the Gauss-Bonnet formula, which tells me this kappa is actually just a topological thing. Right? So kappa is, okay, so it's the average of k tilde on the metric g tilde. It's the same as the average of k with respect to the metric g, but it's, in fact, maybe just write it that way to start with. Okay, so we take the integral of Gauss curvature divided by the area. Okay, and we've imposed that the area is 4 pi, so it's 1 over 4 pi, and the integral of Gauss curvature is just so it's, was it 2 pi times the Euler characteristic, right? Yeah. So in other words, the kappa is just the Euler characteristic of m divided by 2. So something which is purely topological, and particularly is just a constant, right? So I don't have to worry about what happens to this term kappa as things evolve, unlike in the high dimensional case. So 3-dimensional Ritchie flow, this is actually a function of time, which will be changing and so on. But in the 2-dimensional case, it's just a constant. Okay, so that's our normalized 2D Ritchie flow, and we also get corresponding equation for the evolution of curvature, which I won't derive, but it's, you know, we've already derived this in higher dimensions, so I can just use that equation and specialize to this case. So we, for example, we had an equation for ddt of scalar curvature that was just Laplace scalar curvature plus twice Ritchie curvature squared. And if I plug in the equation here, that will give me this formula, ddt of Gauss curvature under the normalized flow. It's going to be Laplacian Gauss curvature plus twice Gauss curvature times k minus kappa, Gauss curvature minus its average. Okay, so that's the evolution of curvature. And that's pretty much all I need, right? So I've got the first equation here, which is the equation for how the metric evolves. And now I've got an equation for how the curvature evolves. And that's pretty much all I'm going to need. Okay, so what can we say about this? The results depend on the sign on the Euler characteristic, right? So we have, I'm going to look at the cases where the Euler characteristic is less than or equal to 0 first, and those are much simpler, as you'll see in a moment. So these are relatively easy. And the Euler characteristic positive, which is really just the case of the sphere, is considerably harder. So we'll get to that a little later on. So first of all, let me show you, there's a very easy argument you can use if you're willing to assume the uniformization theorem. So if we know, so okay, so an easy proof, assuming uniformization, which I don't really want to do, right? I'd like to use the Ritchie flow to prove uniformization, but let's just see how this works. So from a PDE point of view, this is relatively straightforward. In other words, we assume uniformization, which means we assume that our initial metric, g at time 0, is some factor times a metric g bar, which is constant curvature. Okay, so in other words, the k bar, by which I mean the Gauss curvature of g bar, is identically equal to our constant kappa. Okay, so in other words, we've already solved the uniformization problem and found this metric. Then let's write down what the normalized Ritchie flow becomes. So I want to write this now as an evolution equation for just this conformal factor u. Okay, so what is the equation? It's ddtg is minus 2 k minus kappa times g. And so plugging in this expression for g, this will be 2 e to the 2u du dt g bar on this side. And on the other side, I get minus 2, and we got this equation now for the Gauss curvature of g in terms of the Gauss curvature of g bar. That's this one I've got at the top here. So the k will be e to the minus 2u k bar, which is kappa, minus Laplace by u. Okay, and then I get a minus kappa times g, which is e to the 2u g bar. Okay, so what I can read off from that is that du dt is going to be, so the 2's cancel, the either 2u's here cancel. So I just get e to the minus 2u Laplace by u. And then, well, let me write it this way. So I'm going to assume kappa is less than or equal to 0, and then I'll get a minus absolute value kappa times 1 minus e to the minus 2u. Okay, so here I'm assuming kappa is less than or equal to 0. Okay, so what can we do with that? So let me look first at the case kappa equals 0. Okay, so this is the case of a torus, essentially. So we've got an initial metric on a torus, and we're assuming we've got some background conformal metric, which is 0 curvature in this case. So kappa is 0. Then our equation just becomes du dt is e to the minus 2u Laplace by u. Okay, so that's a beautiful equation. It's just a positive function times the Laplacian on the right-hand side. And so I can say straight away from the maximum principle that the inf of u doesn't decrease and the sup of u doesn't increase. Okay, so in other words, I get a uniform bound on u independent of time. Okay, and once I know that, then I know that this coefficient, the e to the minus 2u at the front here, is also uniformly positive. So I get e to the minus c less than or equal, well, minus 2c, I guess, is less than or equal to e to the minus 2u, less than or equal to e to the 2c, is that right? Something like that. So in other words, our equation here is uniformly parabolic, right? And now I can just appeal to some now relatively standard PDE theory and deduce that the u is uniformly Holder continuous. C0 alpha, at least if I stay away from t equals 0. Okay, so away from t equals 0, I get a bound on the Holder semi-norm of u, which depends only on the sup bound for u on this constant c, and the elasticity constants, which are also controlled by c. So if U is uniformly C0 alpha, but then I know that the coefficient eta minus 2U is also uniformly C0 alpha. And now I have a linear parabolic equation with Hölder continuous coefficient, so I can use just Schauder estimates. So Schauder estimates say that the C2 alpha norm of U is uniformly bounded. Again, if I stay away from t equals 0. Okay, now I can just bootstrap. I can just keep differentiating the equation and deduce that U is bounded in CK alpha for any K. Okay, so really we got uniform smoothness more or less for free here, just from the maximum principal controlling U. Everything becomes uniformly parabolic and we're set. Convergence, well, it's actually very easy to prove convergence here, even without any energies or monotone functionals or anything like that. You can just get C infinity convergence straight from the strong maximum principle. So to do that, so let me just do convergence. Let me look at a sequence of functions, let's say on M cross maybe a unit time interval. Okay, so these are just real functions. These are just given by shifting in time. So UK xt will be U at x t minus k. Okay, so what I haven't mentioned here is a priori we don't have short time existence for this flow, but this argument here, the regularity, says that in fact we have existence for all time, right? Because I've essentially C infinity controlled in CK alpha for every K. So if there was some final time, I could just take the limit of these solutions as that final time is approached, and they would converge in C infinity to some limit, and I can just do a short time existence result from there. So the long time existence comes for free. So that means I have these functions UK for any K, and these are now uniformly bounded in CK alpha for every K. Okay, so that means just by Artela-Ascoli, I can find a convergent subsequence. So UK will converge in C infinity to some limit U infinity, and all of the UKs are solutions of this equation star. So U infinity is also, so this is a solution of star on M cross 0, 1. But also I know that, let's see, the sup of U infinity at, let's say, time 0. So what does that mean? This will be the limit as K goes to infinity of sup U at time K. Right? And that exists because we know the sup is decreasing by the maximum, it's not increasing by the maximum principle. So this sup U at time K is a decreasing function of K and bounded below, so the limit certainly exists. But now the sup U infinity at time 1 is the same thing, but now I have U, oops, makes sense to it. This is U at time K, and this one will be sup U, and this time I'm taking, so t equals 1, which means I've got U at x K plus 1. Okay, but this is the same limit, right? So these two limits are the same. So this limiting solution has supremum constant in time. Right? So, but sup U infinity 1, and so in particular, it's the same for every t. Sup U infinity at time t for any t between 0 and 1. But the strong maximum principle tells me that the only way that the soup can be non-strictly increasing, strictly decreasing, is if the u infinity is actually equal to a constant. Okay. So what that argument tells us is this subsequence converges to something which is constant, but that also tells me that the limit as k goes to infinity of sup u k is u infinity, and that's, now I can do the same argument using the infs. So I get inf uk is also equal to that constant, because they'll both converge to the same constant function. And those two together tell me that the u converges, so u at time t converges in C0 to constant u infinity. And in fact, since u infinity is the solution of the equation, oh no, we don't know that in this case, yeah. So we just know that it satisfies star, yeah. All right, so it's converges to a constant, that's what we can say.
Sorry, Ben, why do you know that they have to be the same constant?
Well, all I need to do, so I have a sequence of u's that converge to the constant, and now I can look at the infs of the solutions along that solution, along that subsequence, and I can find a convergent subsequence of those for the infs, right? And then the same argument applied to the infs would, well, yeah, I mean, so that sequence will still converge to u infinity, right? So in particular, the infs along that sequence converge to the same number.
Okay, thanks.
Yeah, so you're just picking the same, subsequence there.
Yeah, gotcha.
Yeah, okay, so we got uniform convergence to a constant, and then the smooth convergence follows essentially for free. You can use an interpolation argument, for example. So I've got bounds in CK, convergence in C0. I say, so I can use, for example, there's a convenient interpolation which would say that the kth derivative, dku, has norm squared bounded by some absolute constant times the sup of u times the sup of the 2k derivative of u, right? And here, this one is bounded, and we've just shown that this one goes to 0. So yeah, all the derivatives will be converging uniformly to 0. Yeah, okay, so it's really very easy argument here. Yeah, okay, the limit, of course, is a solution which is stationary, and that tells us that it satisfies k minus kappa equals 0. And so it's our constant curvature thing. Okay, so in fact, I think also from the fact that it has the same area, you could deduce that u is in fact 0. So but it doesn't really matter for us. Okay, what about the kappa negative situation? So the equation is this one. Okay, so let me just grab that. Okay, so this is actually even better, right? Because this function on the right, well, this function here is looks like this. So it will be positive where u is positive and negative where u is negative. And so, well, I mean, you get an even stronger result from the maximum principle here. So the sup is not only decreasing, but it's decreasing at a rate given by this term on the right-hand side. So you can get from this actually that u has magnitude bounded by some constant times e to the minus 2 absolute kappa t. Okay, so we get, yeah, and the rest of the argument is the same but easier, right? So we get that gives us straight away C0 convergence to, so U converges to 0 uniformly. And the arguments I gave up here really don't change too much. So we get uniform, as soon as the U is bounded, we get uniform parabolicity. This term on the right-hand side is bounded, and so we'll get uniform Holder estimates. And then once we have uniform Holder estimates, it's I have uniform Holder coefficient, and so I can apply Schauder and get C2 alpha estimates and keep bootstrapping. Right? So I get as above, CK alpha bounds as above, and then I get convergence in C infinity to 0. Okay, so that makes the whole situation look rather kind of trivial, but of course I'm assuming uniformization theorem here, so it's, we would like to be able to do it without that. So I'm going to run through most of today. I'm going to spend looking at the kappa less than or equal to 0 situation, but I'm going to sort of look at the proof, which doesn't use the uniformization theorem as an assumption. So in fact, we'll prove this will prove uniformization as a consequence. Okay. So without uniformization. So I haven't talked about the kappa positive situation here, but just to make a quick remark here. So in the kappa positive situation, I get this equation, except that it's a plus kappa, right? Which means you can't really deduce very much useful from this, right? You can't get long time existence in particular. Or I could get, in fact, I could get on any finite time interval, I get an upper bound on U, but you can't get any useful lower bound on U from the maximum principle in the kappa positive case. So we definitely have to work harder in that situation, even assuming uniformization. All right, so the proof without uniformization, and this is essentially what Hamilton does in his paper. So one of the really important ideas here is to use the Soliton identities, right? So sort of philosophy here is that we expect solutions to, the steady state solutions modulo scaling are solitons. So we kind of expect that things should settle down to solitons. Okay, so this is, okay, let me just, as a motivation here, I'm going to quickly run through what those identities are. So let's suppose we have a soliton of this Ritchie flow in 2 dimensions. So that means that K Gij is gradient I, gradient J G, plus maybe some lambda times, gradient I, gradient J F plus some lambda times G. So these are gradient solitons, right? So I'm assuming this is a soliton solution which moves along the flow of a gradient vector field, the gradient of a function f. Okay, so taking the trace, I'll get 2k is, in fact, sorry, let me rewrite this a little bit. I can just choose my sign slightly differently. So kappa, k Gij plus Hessian of f is lambda. Let's take it to be that sign. So when I take the trace, I'll get twice Gauss curvature plus Laplace f is 2 lambda. Okay, and actually now if I integrate that over the manifold, the integral of the Laplacian is 0, and so I end up with lambda has to be kappa, right? The average of the Gauss curvature. So in fact, the equation we have is 2k minus kappa plus Laplace f equals 0. Okay, so this, let's say that's the equation 1, which actually defines the soliton. Equation 2 is this one, which is the trace. Now from equation 1, if I differentiate, I would get, let's say in a k direction, I get k derivative of Gauss curvature times Gij plus a third covariant derivative of f would be 0. And now I subtract the same things with I and k interchanged, so that the terms on the right become a curvature term. All right, so what I end up with is gradient k Gauss curvature times Gij. And this would be RKIJP, gradient PF, right? But in the two-dimensional case, maybe this is just Gauss curvature times metric terms. So I get gradient K Gauss curvature minus Gauss curvature times gradient KF times Gij, and then minus the same things with I and K interchanged. Okay, so if that's 0, then of course, really what we get from that is that the gradient of Gauss curvature is Gauss curvature times the gradient of f, or if you like, gradient of f is gradient log Gauss curvature. Well, at least that makes sense when Gauss curvature is not 0. Okay, so that's one identity that we get. So let me call that 3, I guess. And yeah, and then there's another useful one, which is if I look at gradient I of gradient f squared. Well, so expand that out, this would be 2 gradient kf, gradient I, gradient kf. I can use the Soliton equation up here. That would be minus 2 gradient kf and times k minus kappa Gik. Yeah, and so I get one term which is 2 kappa gradient f, and the other term which is k times gradient f, I can replace by gradient k. So this is minus 2 gradient k. This is I, sorry, Gik, that means these are i's. Yeah, so that becomes gradient I of gradient f squared plus 2, well, I guess gradient of k is also gradient of k minus kappa, so I'm going to write it that way. And then minus 2 kappa f is 0. Okay, so we get this funny conserved quantity here on a soliton, right? So this will be constant on a soliton. So we call that 4. All right. In the two-dimensional Ritchie flow, there's this rather amazing miracle that happens, which is that we can write down an equation for how the potential function evolves. Okay, so here the observation is I can always solve equation 2. Okay, so I can solve equation 2 for f. Why is that? Well, so it's just Laplacian f equals something. I can solve that. You know, Laplacian is just a self-adjoint operator on a compact manifold here. So I can solve that as long as I don't have any component in the null space of the operator. And the null space of the Laplacian is just constant functions. So, so the condition for solvability is that the integral of the right-hand side is 0, which is true kind of by definition here. So kappa is the average of k. So for each time I can solve this. So, but let me approach this slightly different. So solve, I'm going to solve 2 at t equals 0 for f. Okay, and then I'm going to define f for positive times by this equation. So df dt is going to be Laplace f plus 2 kappa f. Okay, so it's essentially just a heat equation. Okay, this is Laplacian with respect to the time varying metric. Okay, so it's possibly slightly more complicated than the usual heat equation, but otherwise not too bad. And the kappa is constant here, so it's this is very simple. Okay, but let's do the computation of this. So if I do ddt Laplace f, okay, well, how do I do that? So remember we had this expression for the Laplacian. So this is ddt of 1 over square root determinant of g, derivative of root determinant of g times gij djf. Okay, so I get one term where I just differentiate through and hit the f. So that'll give me a Laplacian df dt. The metric changes conformally, which means that this product of square root of determinant of g with g inverse doesn't change under a conformal change. That's fixed. So I don't have any term coming from there. The only extra term I get is from differentiating the 1 over root determinant of g at the front. And so that would just give me a plus. Okay, so ddt of g is minus 2 k minus kappa g. So this thing here is going to be a plus 2 k minus kappa Laplace f. Okay, so I get a rather nice equation for the evolution of the Laplacian. And okay, remember we're defining df dt by this equation above. So this will be Laplacian f plus 2 kappa Laplacian f. And now I'll get a plus 2k Laplacian f minus 2 kappa Laplacian f. So this and this are going to cancel. And I end up with just this. So I get Laplacian f and plus 2k Laplacian f. The reason why that is really nice is because we know this nice equation for ddt k, right? That was Laplacian of k plus 2k times k minus kappa. So in other words, k minus kappa and Laplace f satisfy the same equation. And so I can say ddt of Laplace f, let's see, I want Laplace f to be, Laplace f plus twice k minus kappa is Laplacian of the same thing, plus 2k times the same thing. Okay, so and now we're done because it's equal to 0 at time 0, and so by the maximum principle, the maximum doesn't increase and the minimum doesn't decrease, and so that this Laplace f plus 2k minus kappa stays identically 0. Okay, so there's the miracle, right? So we solve this sort of potential equation at one time, and then impose this heat equation, we get a solution for the potential equation at all times. Okay, so now we can use this potential function in our computations. So in particular, so motivated by our Soliton equations, in particular, this last one, this equation 4, right? So motivated by that, let me compute, this is following Hamilton here, so I'm computing d by dt of gradient f squared plus twice k minus kappa. Okay, so what does that look like? So first of all, let's do the first derivative, ddt of gradient if. Okay, so it's just a coordinate derivative when working in local coordinates. So this will be gradient I of Laplace f plus 2 kappa f. That's our ddt of f. Then I have to commute the derivative past the Laplacian. That will give me Laplace gradient f. And the curvature term I get from commuting past is minus Gauss curvature times gradient IF. And then I end up with a 2 kappa gradient IF from the last term. So now if I compute ddt gradient f squared, okay, so this will give me Laplacian gradient f squared minus twice Hessian squared from the first term. I'll get a minus 2 k gradient f squared from the second term, plus 4 kappa gradient f squared. And then I'll get another term from, in this gradient f squared, I've got a g inverse ij up here. So that will give me a plus 2 k minus kappa gradient f squared. Okay, so what I end up with is this. So gradient f squared, and I get minus twice the Hessian, and just plus 2 kappa gradient f squared. Okay. Well, in particular, that's very nice. Particularly if kappa is less than or equal to 0, then I've got straight away a bound on gradient f squared. In particular, if kappa is negative, this would be an exponentially decreasing bound on gradient f squared. Okay, so I want gradient f squared plus twice k minus kappa. So let's see what happens there. So ddt gradient f squared plus 2 k minus kappa. All right, so I've got the equation for k minus kappa just above there. So I get a Laplacian gradient f squared plus 2 k minus kappa. I still get this minus Hessian squared. And I'll get a plus 4k k minus kappa. Do I did that right? What am I missing here? That's right, and then a plus 2 kappa. Oops. Oh yeah, so I get a plus 2 kappa grad f squared, but I'm going to put that in as a gradient f squared plus 2 k minus kappa. And that means I have to subtract off minus 4 kappa k minus kappa. Okay, right. So in other words, I get a Laplacian term, I get minus the Hessian squared term and plus the 2 kappa times the same thing. And these other terms will be a plus 4 k minus kappa squared. Well, that doesn't look so good until I realize that this Hessian was always guided here by the fact that things should hold with equality in the case of a soliton, right? So in the case of a soliton, we know that the quantity we're looking at satisfies a simple equation, has to be essentially constant. And we know that the Hessian term might not be constant, but it is part of this thing which defines the soliton. Okay, so I'm going to rewrite that using, all right, so I want nabla I, nabla j, f plus k minus kappa gij, right? This is the quantity that vanishes on a soliton. And when I expand that out, I'm going to determine which looks like the Hessian square, right? So I get a Hessian squared term, then I'll get a plus 2 k minus kappa Laplace f, and then I'll get a plus 2 k minus kappa squared. Now, Laplace f is just minus 2 k minus kappa. So this is minus 4 k minus kappa squared plus 2 k minus kappa squared. Okay, so in other words, I get the Hessian squared term, and the extra term is a minus 2 k minus kappa squared. Okay, so it's perfect. So in here, I've got a -2 Hessian squared and a +4 k minus kappa squared. That's giving me exactly these terms on the right-hand side. So in other words, I get ddt of grad f squared plus 2k minus kappa is, okay, so I get Laplacian, and I get the +2 kappa term. And then the other ones, I can make 2 gradient I, gradient jf plus k minus kappa gij squared. Okay, now it makes sense because everything in here is things which are constant on solitons. All right, so what does that tell me? Let's see, in the k, let me look at the k less than 0 case. Okay, then in this equation here, I've got a quantity which has, okay, I have a Laplacian term. I have this sort of Hessian type term, which is less than or equal to 0. And this 2 kappa will be a negative constant term. So there's going to be an exponential decay. I'll get gradient f squared plus 2 k minus kappa is bounded by some constant e to the -2 absolute value kappa t. Okay, so that tells me that, well, in particular, the k minus kappa is bounded, right? So the gradient f squared is greater than root of 0. So I certainly have that bound on the upper bound on Gauss curvature. But here we also have a lower bound on Gauss curvature just from the evolution equation for Gauss curvature itself, right? So this is ddt k minus kappa is Laplace k minus kappa plus 2k k minus kappa. This gives me k minus kappa is greater than or equal to some minus c e to the -2 kappa t as well. All right, so I actually have a beautiful bound on Gauss curvature. It's just converging to kappa at an exponential rate. Okay, and now we're in business because that tells me that u, okay, so remember du dt is twice k minus kappa. That goes to 0 exponentially. And so that tells me that the conformal factor u converges exponentially to a limit. Right? So u converges in C0, in fact, at an exponential rate to some u infinity. Right? So in fact, yeah, so we get u minus in u infinity bounded by c e to the -2 kappa t. We don't know much about u infinity at this point, but we do know that the u's are converging. And once I have this much, I can use the regularity as before. So the evolution of u to get higher regularity. Okay, because the evolution would be du dt would be e to the -2u Laplacian bar of u. Let's say bar might be the t equals 0 metric, for example. Then I'll get a term which is -2 e to the -2u k bar, and then I'll get a plus 2 kappa. I think there's no 2 there, sorry. Yeah, plus kappa. Yeah. So once I know that the u's are converging, it doesn't matter too much what this is. It's just bounded. So the k bar is a smooth function, bounded function. I have a bounded right-hand side, and so again I get regularity really with the same arguments before. And so that means the convergence of u to u infinity is actually c infinity. Okay, so that case is easy. In the k equals 0 case, well, this argument doesn't work so easily, but given that I'm solving this potential function anyway, let me just observe if I solve Laplace f plus k g0 equals 0, right? So I know I can do that at time 0. Then that means that the Gauss curvature of the metric e to the minus f g0 is identically 0. Okay, so in fact, we can directly prove the uniformization theorem just by solving this potential equation. And now the argument that I gave before works. Right? So we actually, in that case, it's kind of trivial to see that there is a conformally related metric of 0 curvature. And so my argument actually goes through. Okay, so very good. So that's the k less than or equal to 0 case. What can we say here in the case kappa positive? Not so much at this stage. Okay, so let me just point out what we can get. I do get the same estimate, right? So I get the Laplace. Yeah, I get this exponential bound on gradient f squared plus 2k minus kappa. Okay, except that here, instead of a -2 absolute value kappa, I'll get a +2 kappa. Right, so I'll get an exponentially growing bound on the Gauss curvature. That at least is enough. Again, since I have a good lower bound just from the evolution of curvature, that's enough to say that I have long time existence for the normalized Ritchie flow, right? So I do know, at least I get that much, that the solution of normalized Ritchie flow exists for all time. But at the moment, that's about all I can say. My bounds are all blowing up exponentially as t goes to infinity, and so I can't say a whole lot more. All right, so I think I'm out of time for today, so let me just finish up. So I think what I'd like to do actually next time is talk about the way that Hamilton dealt with the sphere case. Even though there's much easier arguments now, he has this rather nice argument using a combination of an entropy functional and a Harnack estimate, which I think I would like to go through and explain. And then, so at least I'll do that in the case where the Gauss curvature is positive, which is the case that Hamilton dealt with in his paper. Then Chow later on extended that to allow, variable sign of curvature on S2. I wouldn't go through that, but I think, so what I'll aim to do next time is talk about the entropy and Harnack. And yeah, so I'd also like to talk about the isoperimetric profile, which is a different approach, which deals with the sphere case a bit more nicely, but that might mean 3 talks, I think. Let's see where we go. I think we'll see how it works out next time, but yeah, maybe we're looking at 3 talks. Okay, I think that'll do for now.
Cool, thanks for that, Ben. Let's thank Ben for an interesting talk. I certainly enjoyed the opportunity to go through some of those classical PDE results like Schauder estimates. That's always fun when you get to use those.
Yeah, I mean, that wasn't really observed in the original paper. So Hamilton has to work a lot harder. He proves, bounds on the Gauss curvature this way, and then sort of keeps on working more and more to get bounds on higher derivatives, and then has to work back to get convergence of everything to show that the metric actually converges. But it's really, from a PDE point of view, if you're looking at it as just a scalar PDE for the conformal function, then it's actually very straightforward.
Yeah, I thought that was quite nice. Does anyone else have any other comments or questions for Ben? Maybe they've all gone. All right, cool.
Okay,
then
so I can post those, or maybe I can send the notes that I just scribbled down to you, Tim.
Yeah, you can do
post
that.
Up. That might be easiest. Yeah.
Yep. All right. Well, thanks again, Ben. That was great. I'll look forward to hearing some more from you next week.
Okay. Cheers.
Cool.
Yeah, are you
Thanks.
continuing for a few weeks then, Ben?
I think probably I'll aim to do 2 more weeks then. Yeah. So I'll do next week. I'll talk about entropy and Harnack, and then
Oh, yeah.
talk about isoperimetric profiles the week after that.